Yeah, here is it. So that was the energy balance for the heater, talking about of the HDH system. We are assuming a water heater now, and the Qn, the heat added to the water, is resulting an increase in the enthalpy, which can be written as H water 2 minus H water 1, or it can be given as M dot water, Cp water, because the temperature difference is not large. So Cp is constant, and then the temperature difference for the water across the heater. And then again, if you want to look at the entropy generation within the heater, there is no Q here in that expression because we assume all the energy given by the heater has been used to heat the water. So there's no energy loss to the surrounding. And that gives our generation of entropy within the heater accordingly. And the generation of entropy here is basically due to the transfer of heat, due to the increase of enthalpy in the unit as a result of heat transfer. Then the humidifier, when you look at the mass balance of the humidifier, there is M dot water coming in, which is this at state number 2. And it is going to be sprayed here. Part of it will evaporate. It will be carried by the air, which is this part. And the rest is going to be rejected as brine. We are not putting the balance for the mass rate of dry air because it enters and leaves. So there's no point of putting it here. There is M dot air in, M dot air out, and both are the same. What we are interested in is the things that go through a balance or change, which is the water flow rate that enters. Part of it is going to go through evaporation carried by the air, and the rest is going to be rejected as brine. Looking at the energies in and out again, M dot B, H water, this is energy out from the water. This is energy in for the water. This is energy in for the air and energy out for the air. So sigma energy in is equal to sigma energy out, as long as we are talking about steady state condition. To remind you again, to get the enthalpy of the water, all you need is temperature. So you can replace basically this equation by writing M dot B Cp into T3, which is an approximate solution, approximate expression which is accepted, minus M dot water Cp T water 2. This is equal to M dot dry air into, again, to get the enthalpy of the air, you are going to need the temperature of the air and the relative humidity that we assume equal to 1, as you see here. And the entropy generation expression here, second law expression, so that the entropy generation is sigma M dot exit S exit minus the sigma of M dot inlet S inlet. So I have entropy associated with the exit, that is state number 3 for the water, state number 2 for the air, and the inlet will be state number 2 for the water and state number 1 for the air. So that makes the equations needed for the analysis, in addition to the expression of the effectiveness that we talked about last time also, that effectiveness is the actual change of entropy, of enthalpy, divided the maximum enthalpy change within the unit. And this actually applies to the humidifier and the dehumidifier. So to complete the set of equations and have number of equations and number of unknowns are equal, we need to add that expression here for the effectiveness of each component. The gain output ratio, M dot pure water into HFG over Qn. This Q can be whatever. I mean, you can have a system operating by an electric heater, like some of the units that we have in the lab. You can have the system operating by solar energy, so that you can have a solar water collector to heat the water and pass it into the system. Or it can be any sort of waste heat. If you are working beside an air conditioning unit, you can take the heat of the condenser and you can heat water and add it to the system. I added a video last night to the Blackboard that is showing our unit that we have in our desalination lab. And the unit is operating by rejecting heat from a vapor compression refrigerator or air conditioner or a heat pump unit, and the condenser has been replaced. Instead of air to refrigerant condenser, we replaced it by a water to refrigerant condenser. So as the refrigerant is being condensed after leaving the compressor, it gives off the heat to water, and water enters into a humidifier. So that is the source of energy, which is coming to the unit. And we have already done, I'm not sure if I put some of our papers on that unit, but at least I put some, we patented, so I put a copy of the patent in the blackboard as well. This is the expression of the effectiveness. That effectiveness, if you are talking about humidifier, delta H of the water divided by the maximum delta H, which is m dot water in, H water in, minus m dot water out, which is the mass flow rate of the brine, H water out, m dot water in, H water in. This is the inlet, minus the ideal case of water out. Air is coming cold, water is coming hot, so water is going to cool down. The lowest temperature, which is the ideal case, that water is going to be cooled down to the inlet air temperature. So this is m dot brine into H water evaluated at inlet air temperature. That's the H water ideal. And then for the air side, we write epsilon, again, delta H of the air over delta H air maximum. And this is again m dot air, H out minus H in. And then the ideal air enthalpy here is the enthalpy of the air if it is heated to the maximum temperature, which is T water in. So this is how we can determine the ideal conditions here. For the water, it is evaluated at inlet air temperature. For the air, it is evaluated at inlet water temperature. For the water, air is the coldest point in the humidifier. For the air side, the temperature of the water is the hottest or highest temperature within the unit. And this is how that value of the effectiveness is being calculated, and we keep up and we pick up the higher value of them. Is that the best way to represent the effectiveness? Maybe it's not. Sometimes it's not easy to swallow or be convinced of the issue of why should we pick up the higher one. We are talking about basically we are humidifying the air, we are not cooling the water. So the air side would be the one that we should consider, and normally the air side comes to be the highest in this analysis. We have done another analysis recent that puts another definition of the effectiveness. I would probably be able to share it with you maybe next time quickly, but it needs some sort of a substantial information of what's going on inside the unit, because it depends on what's going to happen here. We are talking about water flow in and air flow out, and here we have water flow out and air flow in. And we are looking at values of the enthalpy differences at the inlet and exit. And we call it the enthalpy pinch. What we are doing here, we are calculating it, assuming that the enthalpy pinch is occurring at the inlet and the exit. These definitions are written based on the conditions at the inlet and conditions at the exit of the unit. In reality, what happens is that the enthalpy differences can get closer within the unit. And this is something that we cannot do at the moment because we are doing just a control volume analysis. So at that state, what we need to do is probably follow how the air is going to be humidified here and heated, how the water will be heated and humidified, and look at the smallest difference between them and call it the enthalpy pinch. So that's some sort of a new definition that we have just worked out in the last period of time. We had a couple of applications that appeared this year talking about how the enthalpy pinch can be calculated and how it can be integrated into the entropy, the the effectiveness equation. But I have to tell you that it's not just a straightforward value that you can calculate it, but you need to go through the unit piece by piece to identify where is this point. Sometimes do it graphically, and sometimes you have to do some sort of an iterative technique, or at least go in line by line or piece by piece, as I mentioned here, to reach for the lowest difference of enthalpy. So the point that we are going to consider for our analysis is going to rely on this, the value of effectiveness of the humidifier in the water side, as you can see it here, and the value in the air side, as you can see it here, and we take the highest value or the higher value of both of them. The same thing is going to be done for the dehumidifier. So probably last time I've done that, writing the equation of the effectiveness of the dehumidifier and showing how does it look like. This is taking care of the part which is the introduction part to the HDH system. What we need to do is to go through, I would say it as an example. We need to go through a numerical example. We can solve it together so that you can look at this kind of analysis for the HDH systems in a better way. You can have a closer look into it. I would just at this moment quickly call your names. Definitely, the system provides me with a way that it monitors who comes in and who goes out of the system, but it's just to make sure that you're alert with me. So Rashid Eliami, is Rashid available? No. Abdullah Al-Azwari?
Yes, Doctor, present.
Okay. And Muhammad Al-Ghamdi?
Yes, Doctor.
Ahmed Al-Hussein?
Yes, Doctor, here.
Yeah. Hussein Al-Maslami?
Yes, Doctor, here.
Okay. Hadi Al-Utaybi?
Yes, Doctor, yes.
Hani Al-Rumayh? Hani is not. Okay. Badr Al-Saffar?
Yes, Doctor, here.
Yeah. Saleh Al-Saffar?
Yes, Doctor.
Usama Al-Shahrani?
Yes, Doctor, I'm here.
Okay. Khalid Al-Shamrani?
Yes.
Sultan Al-Suwailim? Sultan? Okay. Abbas Al-Yahya?
Yes, Doctor.
Hussein Al-Yusuf? Okay, and then Dawood Haji?
Yes, Doctor.
Okay. Type. As I mentioned, what we need to look at now is a numeric example.
Probably my name,
Excuse me?
Rashid Eliami.
Yeah, I called you, Rashid. You were.
I can't turn on my mic.
Okay.
Victor,
Thank you.
also
Yes.
you did not say my name.
What's your name? I called all the names. What's your name?
Abdul Karim.
Oh, Abdul Karim. How come I just missed your name? Maybe I assume because you're always there and you're always asking, I assume that you are there. So shukran, Abdul Karim. Thank you.
Oh, Allah يذكرك.
Dr. Muhammad,
No.
I have a question regarding the effectiveness, if you
Again?
question regarding the effectiveness, if you allow me
Yes,
to.
go ahead, please.
So regarding for the water, each ideal, it's going to be evaluated at what temperature exactly? Could you please repeat?
You mean within the humidifier or the dehumidifier?
Yeah, of course, with the humidifier.
For the humidifier. Now, in the humidifier, air comes as hot, water comes as hot water, isn't it?
Yes.
And then it will cool down. So based on that, the ideal condition will be to what temperature water is going to be cooled down. So what is the lowest temperature within the humidifier?
Which is the for water outlet.
No, the
It is
humidifier, what
it's good.
happens is that water comes in as the hot fluid. Let me, for example, show it to you here in this way. Can you see this blank slide in front of us here?
Yes, doctor.
Okay, so that's good. Now, you are talking about basically the humidifier, sorry, let me do something else. I think it's better to share the white screen of Zoom and show it to you, because I would just, I hope that this way you can always keep on remembering it. Now let's, for example, assume that we have so this is, for example, how the temperature changes. In the humidifier, water comes at high temperature, isn't it? And then it cools down. So that becomes T water in, and this is T water out, right? And then it is with air going in a counter current arrangement. So this is going to be T air in, and this is T air out. This is going to make it easy for me when I'm looking at this condition. When I'm looking at the water side, the water's inlet is occurring at the highest temperature, which is here, isn't it? And then it will cool down. Theoretically speaking, if we are talking about the minimum temperature of water ever that we can reach, what is the minimum temperature that you see in front of you here?
Air inlet, the coolest.
Inlet temperature. So T water, in this case, ideal is going to be, as actually it's not T, it's H. So it's going
Evaluated at
to be evaluated H of water. Evaluated at T air in. T out. If I'm looking at H air ideal, now you can tell me by looking at the figure. It should be H air at, air is going to be heated. So what is the highest temperature?
water inlet.
Yes, T water in. So this is how to determine the ideal cases. For water, it's going to be cooled down. So the ideal case is the lowest temperature in the whole system, which is this. Air is going to be heated up. So the maximum temperature air can reach for is this. It will not reach to this value, but we are evaluating, we are doing a comparison between the actual change of enthalpy to the maximum one. The maximum is the maximum ever, that to realize this maximum, we need an area which is equal to infinity. But it's one way to see how effective this unit is performing. For packed bed humidifiers, we expect a value of the effectiveness to be in the order of 70% or maybe 80% at most. Now let's look at, so this is for the humidifier. What about the dehumidifier? What enters in and what leaves? In the dehumidifier, air enters at high temperatures and leaves at a lower temperature. Water inlet at the lowest temperature and leave at a higher temperature. If I'm talking about effectiveness for the air side, and I'm looking for delta H maximum, it should be this temperature of the inlet air, because this is the hottest here, minus the lowest temperature ever. So the H air ideal is going to be H air at, air will be cooled down.
Water inlet.
So it should be at T water in. And I'm looking for epsilon in the water side. Water is going to be heated here because it will recover energy from the air. So H water ideal is going to be H water at, water will be heated. So what is the highest temperature here? Inlet air temperature. So if you are solving a problem and you got to a point where you don't know which is which, what you do is just put this, because both of them, we looked at the humidifier and the dehumidifier as some sort of a counter current heat exchanger. It's a heat and mass exchanger. Water is going this way, but air is going that way. So it's a counter current. Then this is the kind of profile that you studied previously in heat transfer. The same thing applies here for the dehumidifier. We have water coming in tubes, but it's going up. It's going in this direction.